Welcome to my second section, Deep Learning for Images with Keras. In this section, we're going to create and train a convolutional neural network using Keras. I will give you an overview and demonstration of image augmentation, train a model using image augmentation in Keras, and finally, I will show you how to use Keras to classify videos. This video is about creating and training a convolutional neural network using Keras. I'm going to explain to you what a convolutional neural network is. I will show you how to build and train a convolutional neural network with Keras. First, let's understand how computers see images. On the left is what a human would see, picture of dogs. When we pass this into a computer, the computer doesn't see the dogs in the same way. It sees a set of numbers related to the various pixels in this image. Here is a hand-drawn image of a number 8, 28 by 28 pixels. There's 784 pixels in this image, and a computer sees all of those pixels. As the image gets close to where the 8 is drawn, the pixels change in value, and that allows you to understand where the 8 is. Now, if you imagine each of those pixels as an input to a deep learning algorithm, the algorithm has to take all of those inputs, apply weights to each of them to figure out what's the best set of weights that'll get us to the output of number 8. It'll do this across all of the images, start to learn about them. Now, the one challenge here you can imagine is that the bigger the images and the bigger the datasets, the number of features become very large, and this makes it harder and harder for deep learning algorithms to work. But with convolutional neural networks, make it a little bit easier with some techniques they have built in. A convolutional neural network is essentially a deep learning method around image recognition and classification. It essentially works by taking newer features based on smaller subsections of each image that preserve the proximity around them. This allows it to be a lot more effective about learning about images, especially with larger datasets. The term convolution is a mathematical operation that says data takes a dataset and is compared step by step by the entire span of another dataset. Here is a typical architecture of a convolutional neural network. You have your input image, and convolutions are created, small subsets of features from that image, built out into feature maps across the different layers. Over time, these are consolidated into a final output layer to get to that classification. One big challenge of machine learning against images is that in order to get decent results, you often need a large number of images to start with. Having a large number of images also requires you to have a large amount of computing power. Both of these things can be a challenge in order to train a machine learning model. However, transfer learning allows you to fast-track your learning process with a smaller subset of data and less computing power. This allows you to take pre-trained models that may have been trained against a larger dataset with bigger computing power and use them as the starting point to train your model. This simply allows you to take a source model that maybe has been trained against a vast dataset by a large organization that has the power and the resources to do that, and then use that as the basis for your model, allowing you to bring a smaller set of images to be able to learn about those. There are various ways you could use this pre-trained model directly as a classifier without having to do any additional training. You could use it to extract features standalone from your images to do pre-processing on those, or integrating it into your model training either as an integrated feature extractor or to initialize the weights in your model. Let's take a look at building our first convolutional neural network with Keras. So this is a notebook I prepared to walk you through and demonstrate how to do image classification in Keras. This will build a simple image classifier over some fashion items. First, we will import Keras. As you can see, it's using TensorFlow as the backend. Next, I'm importing a bunch of other packages from Keras to allow us to build out our convolutional neural network. You will notice under layers, there's various types of layers that we'll use when we build out our model architecture. One of the key ones is Conv2D. This is Keras' convolutional two-dimensional neural network. There are other types as well. We're using Adam as the optimizer, which is built on top of the SGD, or Stochastic Gradient Descent Optimizer, and is used more commonly in computer vision problems. We'll also potentially do some pre-processing, so let's import the image data generator here. For our dataset, I am using the Fashion MNIST dataset built into Keras. This is an extension of the classical MNIST dataset. MNIST is a common dataset that basically contains handwritten characters from 1 to 9. You can build a convolutional neural network to predict what is that handwritten character. This dataset is a little bit more complex than that. It contains fashion items, t-shirts, shoes, trousers, etc. And we use the model to be able to predict what category the item belongs to. Since it's a little more complex, it makes the problem a little bit more interesting. Finally, I'll import a utility here to convert our labels to categorical. This basically one-hot encodes our values in the labels. What this really means is we're creating a binary matrix of the values in our labels. Loading the fashion MNIST dataset essentially will load a set of images, about 60,000, that fit into one of these categories. There are 10 categories in the set, from t-shirts through to ankle boots. Calling fashion MNIST.loadData here will load that data, and because it's a pre-built dataset, it's nicely split into training and test data, as well as features and labels. If we take a look at the uniqueness of the labels, we can see they match 0 through 9, as we'd expect. We can just print out the shape of our training data here, and we can see there are 60,000 entries in here, each of 28 by 28 pixels. Each of the pixels are a feature for the input. For the test dataset, there's around 10,000, so we have a training set of 60,000 and a test set of 10,000. Now, one of the first things I want to do here is normalize the values that are stored in the 28 by 28 arrays. This allows the machine learning program to discount any big gaps. To do that, initially note that the values are stored between 0 and 255, and we just normalize them by dividing everything by 255 to rescale them around 0 and 1. So we'll go ahead and do that using the NumPy package. Matplotlib is a nice package for plotting and drawing things within Jupyter Notebooks. Here we've just defined a function to plot out the images, and we'll go ahead and plot out the first 10 images from our training set. So here you can see this is what those images look like. Get an idea, you've got a boot, got a t-shirt, a dress, etc. Now we will need to build out a convolutional neural network. This is defined in the build model function here. As before, start with a sequential model. Now the first layer here is that conv2D, which is the convolutional neural network layer. This is the input layer, and the input shape is 28 by 28 pixels, as defined here. We then define a couple more layers, and you can play around with this as you get more advanced. And finally, we bring it back down to the final layer, which has 10, which is the number of labels that we want to get and predict. We compile this together using model.compile, and then we return that model architecture. Now, before we pass in our data, we do need to reshape it, so we'll just go ahead and redo that here, and we'll also need to convert that set of labels to categorical. Using toCategorical will one-hot encode those labels to a binary matrix for us. And print those out to see what that new shape looks like. We'll do the same thing for the test data. When that's complete, you can go ahead and build the model and then call model.fit to train the model with the data. Here I am training it over 10 epochs with a batch size of 32, using our test data as the validation dataset. Each epoch will result in accuracy and loss values, and I'll store those in the training history metrics. When you go ahead and execute that, depending on the power of your machine and the number of epochs you have, this may take a little bit of time to train. Once it's complete, let's take a look at the history. We can go ahead and plot that out on a graph to get an idea of how our model performed. As you can see, the accuracy started to increase rapidly for the training accuracy over the epochs, and it started to increase slightly for the test data as well, as we'd expect. In addition, we notice the loss really dramatically decreases for training. For tests, not so much. Maybe we need to train it over more epochs. Finally, let's just show how you can now attempt to predict, passing in a new image to see what value it classifies this as. Let's take one of our test data's images, plotting this out. Maybe hard to see here, but this is a sandal. Let's pass that into our model to see how it performs. Here I've defined a simple array of the labels. I pass in that prediction. The prediction returns sandal as the output, so it accurately predicted the output and classified this image correctly.